Hi, I'm Pete Kane. I'm an RF engineer with Agilent. Over the last decade, I've been involved with testing lots of different sorts of radios, from the frequency hopping of Bluetooth to MIMO in wireless LAN, and OFDMA in WiMAX and LTE. Common theme with this kind of radio is the sophisticated messaging that's used to control the link between the mobile and the base station. Trouble is that this messaging can fail in a variety of different ways, and that can result in poor battery drain in the mobile, throughput that's less than it should be, or other kinds of failures such as reduced capacity for the channel as a whole. And that's why I'm here today. I'm going to describe the use of a new tool, 89600 WLA, that will allow us to both capture the messages and uncover their contents to understand what's happening when the link isn't operating the way we expect it to. We'll be using the PXT to act as our base station, and it will work with a mobile connected with a laptop. The signals will be captured with the MXA signal analyzer, and we'll take that data and decode it in WLA. There's going to be two examples that I'm going to show you. The first will be around the cell attach process between the UE and the eNode B. And this is a really important point in the transactions between the two, because there's really important information that's sent just at the time that that process takes place. That's the first example. Second example involves one of the feedback loops. There's 6 in LTE. The one that we'll look at is a downlink transmission, and this involves the use of HARQ processes, hybrid ARQ. If they're not working properly, it means that the throughput for the mobile can be less than it should be, or else the capacity of the channel as a whole is less. And here I'll use the MXG signal generator to create distortions that allow us to test the response of the system when that's taking place. I think that 89600 WLA has a lot to offer in exposing what's happening when things aren't going right. I hope you find the video helpful. In this example, we're going to capture the cell attach process between the UE and the eNode B. The reason we'll do this is because there's a lot of important information sent in the messages from the base station, here the PXT, down to the UE at the very beginning of this process. We've got the PXT acting as a base station, and it will log this too, but we don't always have that. The mobile is over here on the laptop. We'll capture the signal using the MXA, and I've got a device here that is going to act as a power detector for the signal coming from the UE. So as soon as the UE starts to transmit, we should see the trigger take place and a few messages appear on the screen here. There we go. The process happens very quickly in LTE, in less than a quarter of a second, and now we've captured the data in the MXA signal analyzer. Let's look at the post-processing in 89600 WLA software.
Before we look at the first example, let's understand where the message is going to come from and how we can recover them. This picture shows the layers of the protocol stack and how 89600 WLA works in conjunction with the existing vector signal analysis. The messages that we're interested in the first example come from the top of this chart from the radio resource control, and they flow down through the channels shown before they're transmitted. 89600 WLA allows us to examine these messages in the form of a message log and then the detailed contents of those messages. If the UE has been given an uplink transmission allocation, that's shown at the bottom. Two other parts of the tool that are going to be very helpful are a table showing the uplink configuration parameters. Those come from several messages, including system information block and the radio resource control, and the ability to plot activity over time using Microsoft Excel. There are many feedback control loops in the LTE link, and this is one of the features we can use there. The test configuration is straightforward. We've got a base station emulator in the top left feeding the UE under test, and the MXA signal analyzer will capture the IQ record for analysis. The question we want to answer is whether the configuration is correct for the mobile, and if it isn't, for example, the throughput measurements may not respond as expected. I'm going to use a trigger on the random access channel coming from the UE. That could either be a simple power detector shown here or a second MXA. If I use a second MXA, I can always capture the uplink signal as well. If we go to the VSA and MXA screens, I've got a recording here that I'm going to run through, and I can see already that the VSA can demodulate it successfully, which is an essential starting point. As I use 89600 WLA to start the processing, the messages begin to appear, and I can click on these to find out what the contents are. This first example is with the random access response, and it's showing me there's a timing advance offset, initial offset of 2 microseconds. We can see there are occasional uplink allocations being given in this process as well to the mobile at the bottom of the picture. We're very close to coming to the end of the recording. We've done that, and I can see that a number of messages have been recovered. I'm going to be particularly interested in what's come from the RRC connection setup message, because that does contain much of the configuration information. If I want to look in the details, I can scroll through this window, but the chart here brings out that information much more conveniently. So here I can see the shared channel configuration, the control channel. This all looks okay. What I was suspicious about was the CQI reporting, because I had a channel interference, and in fact what's going on here is that all the information is left blank. For some reason the configuration with the setup hasn't resulted in CQI reporting instructions being given. So this would then explain why there could be problems with the connection.
Okay, well, we've seen the messages contained in the cell attach process. Now let's move on to one of the control loops. This is going to be involving the downlink throughput and the hybrid ARQ processes associated with that. I'm going to get a test running here, which is going to be sending downlink traffic to the mobile. And we're seeing on the MXA signal analyzer the traffic and it's 64 QAM. Everything's good at the moment, but now I'm going to use the MXG signal generator to create little pulses of noise to interrupt those processes. And that's what we're going to analyze next. If everything's right, the retransmission should be quick and sweet, but sometimes things just don't work out that way. Let's go and now have a look. We've captured the signal again. Here we go. We just press the red button. The MXA will get it, and we'll go and post-process it with 89600 WLA.
In the second example, we're going to look at a very different point in the stack. It's down here, shown on the bottom right, and it's to do with the HARQ processing, which goes through the control channel. The reason we're interested in HARQ processing is fundamental to the throughput on an LTE link. Packets are broken up and transmitted over multiple processes. Each one of these, if the UE is unable to successfully recover a signal, it issues a NAC, or negative acknowledgement. When the ENO-B transmits the data again, it increments the redundancy version, and it goes in a sequence 0, 2, 3, 1. It does this for all 8 processes that it may be using to minimize the latency. So if these things are going wrong, latency can increase or the throughput can decrease. The test process configuration is the same initially as we started with. In this case though, in order to stimulate HARQ activity, I'm going to inject bursts of wideband noise from the MXG generator. The question is, do the HARQ link processes respond the way we would expect, or are they otherwise limiting data throughput? The nature of the bursts of noise is shown in the bottom right, and it's very short bursts every 5 frames or so, which means that any response to the noise should be over and done with. We can examine each activity one by one. If we go to the recording of the test signal and follow it through the last stages of the analysis, we can see 89600 WLA is working through it again. The number of messages in this case is actually much smaller than before because we don't have the connection establishment. The process is now complete, and what I'm going to use is the graphing feature that I described before. I'm going to select the downlink throughput, and the information I want to analyze is just for the traffic and the acknowledged data. When I then bring up the Excel chart, it plots all the information, and we can see that there's a couple of key aspects to this chart straight away. The lines that go diagonally are indicating the throughput. I'm injecting only very small bursts of noise, so I wouldn't expect a great deal to happen to that. The slope represents the throughput. It's the number of bits per unit time. The other part that is fairly obvious is this regular pattern shown here, and this is the change in redundancy value from 0 to 2. This is what we're expecting. However, there's other parts of the chart where there's much more activity happening, and let's now go and find out what's taking place there. If I start by using one of the points, we can see if I hover over here for process 6 and go to that point in the recording, I can switch to use the error vector time view. So this then now shows us the exact point in time where that noise burst happened, and that was what caused the change in redundancy version from 0 to 2. So that's what we're expecting. If I go to a later point in the chart where we have more activity and it's not so regular, then again we move to that point in the IQ record, and as well as the noise burst, we've also got some other activity here. This could be noise coming through conducted. This needs to be examined because that's what's caused that flurry of activity. And all those redundancy version changes imply extra capacity is being used in the link for those retransmissions. So that's happening unnecessarily. There's another situation a little further on that's a little different. And again, I'm going to move to that point. And in this case, hovering over, I can see it's process 2. In the error vector time, we don't see anything going on. There's no noise burst at all. I'll move back one step, following down the chart, nothing there. Back again to the previous frame, still nothing. And then finally, one more step, we go back. We do see a burst of noise, but if we look at the VSA responses here, that's happening in subframes 0 and 1 when heart process 6 and 7 are the ones that are active. So this process that we've seen here is a different thing altogether. It's nothing to do with the RF. There's maybe something happening in the baseband, a state that's got stuck. And so we've used the tool both to discover issues that we do expect, errors, two different sorts of errors that were not anticipated at all. And it's an indication of how the tool can be used to highlight failures that will affect throughput.
In those two examples, we saw how 89600 WLA software found things we weren't expecting. Using it can increase your confidence in the understanding and the operation of your system. To find out more and to try the software for yourself free of charge, visit the URL below. Otherwise, I hope you found the video informative, and I look forward to seeing you again soon.